I can see the screen and I can hear you.
Great. So let me get started talking about my work on boosting scientific knowledge discovery by harnessing scholarly literature. So what you see here actually is a copy of the first ever scientific journal published back in the year 1665. And this journal published on just about any subject that existed back then, from planets in outer space to whales in the ocean. So if you were looking for scientific knowledge back then, that journal would be the place to go. But today, you'll use a search engine like Google Scholar, and you're much more likely to come up with something like this, a whirlwind of research papers. Now, this kind of flood of information has serious impacts for science. It creates information overload, making it hard to keep track, and I'm sure we can all identify with that. This leads to inefficient knowledge sharing and discovery, which creates these isolated silos of scientific knowledge. And the more isolated these silos get, the harder and harder it is to share and discover knowledge. So this kind of vicious cycle leads to a research tunnel vision, an inwardly focused scientific culture. And this means that it's increasingly hard to discover ideas outside our narrow bubbles of knowledge. So the question is, what opportunities for solutions, directions, inspirations, and breakthroughs outside our bubbles are we missing? And can we build computational systems to help us find them? So my vision is to build these computational approaches that harness our collective scientific knowledge embedded in the scholarly literature to augment and scale discovery. Looking at the literature not so much as a pile of papers where we dump our ideas, but more like a potential database of scientific problems and solutions, directions, and inspirations that can be leveraged to help people across the sciences throughout all parts of their work, from creating ideas to making decisions by tapping into scientific knowledge in the literature. So that's the vision, but there are some fundamental challenges on the way. First, the literature is large scale, unstructured, with complex ideas described in complex language. Another dimension to this complexity is just the underlying huge space of hypotheses you can explore in science. Think about all the different directions you can explore for all the different problems out there. For example, I've recently been working on biomedical knowledge graph completion with applications for drug discovery, where you have these huge combinatorial spaces of things like compounds, drug targets, genes, proteins, etc., and you need to predict missing links in this space. Another example that I've recently been working in is drug synergy, where again, you have these huge combinatorial spaces of potential combinations of therapies to try. But still, our current way as researchers and scientists for interacting with all this wealth and complexity in the literature is very, very limited. In particular, most of us interact with the literature via standard keyword search engines, where we get back these long lists of results with many papers, making it very hard to discover new ideas, to make connections across the literature. And finally, there's the important fact that science is a human process with social and cognitive biases that dictate who we work with, what we work on, who we cite. And these biases propagate all the way down to those search engines we use to discover knowledge. So in order to address these challenges, my work develops novel approaches for search and discovery with new methods in information retrieval, information extraction, data mining, human-computer interaction. So for example, I've built a search engine for finding inspirations for creative solutions for problems. So your input is a description of a problem and the output is all kinds of novel solutions based on finding analogies across distant areas of science and technology, or finding novel authors who make you think of new ideas outside your bubble of knowledge. And to develop these new approaches, often need to design new AI settings and new models in areas like weak supervision, knowledge graph construction, link prediction, and textual matching. So for example, we've built a new NLP task and models for learning to link scientific concepts across diverse literature and diverse communities that use very diverse language that can sometimes refer to the same thing. So for example, take machine learning and statistics. You have terms like false positives and type 1 errors, which actually refer to the same thing, even though they look very different to a machine. Or class imbalance and skewed label distribution as another example. On the other hand, things like kernel and operating systems and kernel and machine learning, or network architecture in systems and network architecture and deep learning refer to different things, although they look exactly the same, which is one of the main challenges in processing this diverse language in scientific papers. In today's talk, I'm going to talk about biomedical knowledge discovery. And I'm going to focus on a recurring central theme to my work, which involves extraction, interaction, and prediction. Structuring the literature by automatically extracting meaningful representations of it, then using those representations to power new modes of interacting with the literature for discovering new knowledge, and then finally leveraging structures to predict new knowledge based on existing knowledge. And I'm going to show two lines of work that touch on this. First is building novel scientific search engines powered by information extraction, and then retrieving knowledge for enhancing biomedical or biochemical predictions. So let me start with the first, extraction and interaction. And one of the main problems with extracting information, meaningful representations across diverse literature is the fact that literature is so large scale, diverse, and complex, as I've briefly shown. In particular, existing scientific information extraction models in NLP really only a fraction of all the potential entities and structures you can think of to potentially exist in the literature. So here's a kind of semi-random example I recently saw from a paper from about a month ago, where the authors say that immune correlates of protection are important to understand the immune response to the SARS-CoV-2 virus, and existing NLP models trained in biomedical literature do not identify these things. So the authors develop a model to extract them. Now, this is important and great, but one problem, and this is kind of one example out of many examples, and the problem here is this approach of tailoring a classifier or an extractor for each new concept or term, or not to mention a relationship that crops up, is not feasible across so many potential types of entities and relationships in the literature. And this is only in biomedicine. So if you think about extrapolating and going across all scientific literature, it of course completely explodes, not to mention that the literature evolves rapidly with new concepts and new types of relationships being introduced. So one of the central goals of my work is to develop broad coverage extraction of useful structures, useful representations. Representations that are in some sort of sweet spot between being expressive enough to be useful, but also simple enough to extract across general literature. And I'll show two examples. First is based on observing that across science, researchers think in terms of causal relationships, in terms of functional relations, mechanistic relations, and interactions. So let's see some examples to illustrate how broad this is. So for example, this could say that certain medical procedures can result in airborne transmission, an example of a causal relationship. Or you can have functional relationships that discuss the use of things. For example, a physics-based model is used to investigate airborne transmission. You can also think of mechanistic relations like physical actions. So a certain compound binds to a certain active site and displaces some cofactor. And then finally, we have interactional relations. So that same compound interacts with some substrate site. And these, of course, are just a few examples of a abstraction that we call mechanisms, which has really a broad reach across the sciences in diverse disciplines. And we develop a new information extraction schema and expert annotated data set for these graphs of mechanisms that capture causal and functional relationships. And we apply this idea, this schema, first to the space of COVID-19 literature to build a knowledge base of COVID-19 mechanisms. And we focus on COVID-19 not only because it's important and timely, but also because it's a great test bed in being highly diverse with hundreds of thousands of papers with multiple disciplines coming in. So we train a model and we extract this knowledge base automatically across all these papers. And then this knowledge base, which is also available online, can be searched to find all kinds of relationships. So for example, you could find all the functions or uses of deep learning for drugs. Or you could find causal effects between entities. For example, the causal effect of heat on the SARS-CoV-2 virus. Or kind of open-ended query where you can retrieve all entities that act to block viral binding. And finally, just as another example of the diversity, you can find all kinds of diverse impacts, like the impact of COVID-19 on economic prices. So we gave this knowledge base to diverse experts and also to medical doctors and hospitals, asking them to search for clinical causal relationships. And one of our key nice results is that we were able to obtain much higher utility and quality than the kind of go-to biomedical search engine, PubMed, for this kind of search for causal relationships. Now we take this model that we trained on COVID-19 papers and we predict on general papers across different diverse areas. First, we observe quantitatively a relatively small drop in accuracy, which is encouraging, and again attests to the generality of this schema and also to the breadth of COVID-19 literature. And then also we look at some specific examples and really discover very interesting and useful potential connections. So for this presentation, I took some very recent papers. One of them, for example, is from Martin Burke from this institution. And this is a paper from about a month ago in chemistry. You know, we can see we can take this rather complex technical abstract and start breaking it down into these rich graphs of causal and functional relationships that can provide a lot of interesting information. Again, this was trained in a completely different domain and applied with a zero-shot, no supervision on this domain. Here we can traverse the abstract a bit further down and see that we can get these very rich graphs that capture potentially useful information. Now let's go a bit even further and go to a computer science deep learning paper. In this case, it's a paper that's related to audio and speech. And we can see that we extract potentially very explicit structured representation that can be used for a lot of different applications. So for example, this model, we now know that it synthesizes speech waveforms. And this improves the quality and consistency of the output waveform. And it does so by applying a combination of multi-scale waveform generator and a hierarchically nested discriminator. And in combination, this learns multiple levels of acoustic properties. And you can think about all the different uses for such a thing. For example, by searching the literature for in a structured form, exactly like in that knowledge base I showed, also finding all kinds of novel connections between methods and synthesizing them and finding interesting analogies between methods. So multiple uses for this representation for exploring the literature. Okay, so I showed you one example of extracting known information, and I want to show another example of extracting indications of what is unknown. So to show you what I mean, let's take, for example, a researcher. And this researcher is interested in the SARS-CoV-2 virus and the ACE2 receptor. Now, this relationship between the virus and this receptor is, of course, being studied heavily in the past 2 years. And this researcher is now interested to know, what don't we know about the relationship between ACE2 and the virus or the disease? What interesting directions at the edge of science, a kind of frontier of science, are out there that could be interesting and important to explore? And of course, this doesn't have to be only an individual researcher. You can think of funding agencies like the NSF or NIH, looking to prioritize areas for research by understanding where we know less and where we have more difficulties and uncertainties. So if you would search for this relationship on PubMed, you're going to retrieve a lot of known knowledge about ACE2 and COVID-19, because again, it's been heavily explored. So the goal here is to help researchers keep track of difficulties, uncertainties, gaps in knowledge, and also emerging hypotheses and directions. And we do this by creating a search engine for discovering what we call challenges and directions, where in this search engine, the input is topics or keywords that you're interested in, like COVID-19 and ACE2. And then the output is sentences that mention problems, limitations, or hypotheses and directions. And this is also available online to explore. So for example, using again COVID-19 and ACE2, using our search engine, you can now retrieve statements of possible roles of ACE2 and all kinds of things that are more uncertain, more initial, more preliminary, like the possible role for this receptor and the pathogenesis of liver damage in COVID-19. Now, technically, to build this, we first, again, create an expert annotated data set for these challenges and directions, and then train a model to extract these sentences across hundreds of thousands of papers and index them in our search engine. And we find that this model, in terms of precision and recall, does very well. And also, again, in terms of zero-shot generalization across biomedical papers and even across AI papers, does substantially well, again, due to its abstract generalizable schema across the sciences, and also the diversity and breadth of COVID-19 literature as a training set. So to show again another example for this, a very recent paper from about 10 days ago, I think, from David Baker and Eric Clavens, related to proteins. And this is related also to biology and to AI in the exploration of protein structure, etc. And so let's see what challenges this paper mentions. And this is from the full text of the papers, not only from the abstract set. So one challenge is, okay, space constraints on some library chips, so we were not able to evaluate something, or generalization to new classes of proteins with all kinds of different sizes or topologies is not so good because of limited training data or limitations of the model that does not explicitly consider the 3D structure. So this already raises all kinds of potential things to work on, readily accessible and searchable. There are also directions. So for example, the authors conjectured or reasoned that there are all kinds of potential latent factors that could also affect cleavage resistance, or that the extended version of their model might be able to help speed up discoveries, etc. I also wanted to show an example of the rather impressive ability of the model to ignore false positive, potential false positives. So here we see that the sentence has all kinds of kind of suspect keywords like decreases in stability or limited analysis. But when you actually read the sentence, you see that the what the authors are saying is that to evaluate the model's ability to predict decreases in stability, the analysis was limited to specific cases. So this is not a challenge, as the model correctly identifies. In terms of the utility of this representation, first we see the researchers, diverse researchers with diverse backgrounds who used our search engine were able to obtain knowledge and rapid knowledge, again, much more than with the PubMed search engine. And then with 9 medical doctors working in a large hospital and also involved in research, we obtained much higher satisfaction with our system than with PubMed for this kind of important knowledge discovery. And of course, for all the stuff that I just mentioned, we have resources available online, like the data, the model, code, and the search engine. Okay, so and the second part of this talk, I want to show you some work that goes beyond extracting information to predicting information. So say, for example, we have a researcher who's interested in predicting whether some drug can treat a disease Y. And this is not a known relationship that just exists somewhere in the literature. You need to predict a new relationship. Or whether a specific patient coming into the hospital is at a risk of a specific outcome. Now, as a kind of rough abstract sketch of how we as humans may do this, I like to think of this notion of prediction-guided knowledge retrieval, where we retrieve knowledge from our internal bank of knowledge in our minds, but we also need to sometimes increase our confidence or to obtain more knowledge to fill in our gaps by retrieving external knowledge from predominantly the scientific literature. So of course, this is an abstract, grossly simplistic representation of how this actually works in humans, but it's illustrative and useful to guide this notion of leveraging that information in the internal and external knowledge and using it to make predictions, in this case, these binary predictions. And now this inspires a vision that I have of augmented knowledge retrieval, where you can think of a system that is aware of the things you want to predict, like the risk of a specific patient, and then retrieves external knowledge guided by a specific predictive task to enhance our ability to make this prediction. And our recent work takes some initial steps toward this vision, and I'll show you two of these that involve tapping into the literature in all kinds of ways to augment scientific predictions. First, in terms of biomedical hypothesis generation, and then in terms of clinical outcome prediction in hospitals. And in particular, we ask two questions here. First, can neural language models trained on biomedical corpora, like for example, millions of papers in PubMed, be leveraged for predicting new links in biomedical knowledge graphs? And secondly, can we enhance prediction of clinical outcomes in hospital patients by retrieving patient-specific medical literature? So I'll start with the first question revolving around biomedical knowledge graphs. We focus on biomedical knowledge graphs related to the clinical questions around drug discovery, like drug targets and diseases, etc. For example, one of these is on drug disease pairs intended for drug repositioning research, where you want to find off-label uses of drugs. Now, the kind of standard approach that I'm sure a lot of you have heard of for completing knowledge graphs is basically by learning a neural representation, nodes and edges in a way that captures graph structure, and then using these representations to predict whether a relationship between two entities, like a specific drug and a specific disease, exists. Now, in this work, we look at that graph representation too, but we also look at something that is not really being explored in this scenario and setting, which is taking a literature language model that's trained on biomedical papers, and seeing if we can leverage that information and a textual representation of entities in our knowledge graph to augment the ability to make these predictions. And we first observed that across our test data, we see some really distinct subsets of the data where each one of these, let's say, modalities of graph and text perform better. So this suggests that they could have complementary strengths. And to explore that, we conduct a study of all kinds of approaches for integrating the language models and the knowledge graph embeddings. So in a nutshell, without going into too many details, the way this works is by taking these relationships or tuples, triples that we care about, feeding them into the language model and to the graph-based model, and also encoding them with all kinds of feature representations that capture the graph structure, but also the textual information. And then using that to learn an input-dependent weighted average that adaptively assigns to either the graph representation or the natural language representation based on each input's properties. This can also kind of adapt it to a router setting, where the model decides adaptively to route each candidate to triple, either to the language model trained on scientific papers or to the internal kind of graph-based model. What's another interesting thing we explore is routing across multiple language models trained on different subsets and different types of scientific knowledge. And of course, in the paper, we have a long table of results, but here's the two core takeaways. First, integrating the text and the graph provides substantial improvement in accuracy over just using any one of them. And then also looking at multiple language models and routing or adaptively weighting across them further boosts results, which is an encouraging finding for the potential for using the information latent in these literature-trained language models for biomedical hypothesis generation. Secondly, and finally, I also want to quickly show another approach for prediction. And here we're focusing on predicting clinical outcomes of intensive care unit patients, outcomes like in-hospital mortality or prolonged mechanical ventilation or length of hospital stay. And we do this by taking the well-known MIMIC dataset, and then we look at admission notes, the notes that a patient has when they come in to the ICU. And then we want to predict what will eventually happen. Like, will there be in-hospital mortality, or what will the length of stay be? Will it be very long? And importantly, this is an early stage prediction by prediction only based on admission time information. So we design a system which we call BEEP, for biomedical evidence enhanced prediction, where we take the admission note and then we take literature that's related to each specific patient. So we retrieve patient specific information from medical literature that matches the admission note, and then we combine these two sources to enhance our prediction. So let's look at this example here. We have a 49-year-old male with refractory hypoglycemia, and this patient is a type 1 diabetic. And then we retrieve a paper that says that, this is a real example, but we retrieve a paper that says that severe hypoglycemia is not associated with an increased risk of mortality in adults with type 1 diabetes. So this indicates that this specific patient who has hypoglycemia and is an adult and type 1 diabetic is actually not at increased risk of mortality at the hospital. So this enables us to make a more accurate prediction, in this case, that the patient is more likely to survive. In a nutshell, the way this is built is based on these two kind of modules. First, on retrieving relevant literature to the patient, re-ranking it and weighting it adaptively so we can predict the final outcome. So the model learns to assign different weights to retrieve literature in a manner that increases predictive accuracy of the specific task or specific question we have for a patient and some outcome we're trying to predict. In terms of results, we see some substantial boost in common metrics over strong state-of-the-art recent baselines. And interestingly, we also look at the high confidence predictions, these cases where you'll raise an alert only when the model is more confident to save physician time and avoid alert fatigue, which is an important problem in this space. And what we observed here is a really big boost over the state of the art. So for example, in terms of predicting mortality, we see a huge increase in precision with only a comparatively small drop in recall. And finally, we also conduct an analysis trying to find where did the literature substantially help. So this is kind of similar to that example I showed earlier of the patient who is an adult and has type 1 diabetes and hypoglycemia. And we explore more in depth in what cases does the retrieved literature help. And we see all kinds of interesting scenarios where different types of matches between the literature and the patient are able to dramatically increase the model's confidence and kind of sway it in the right direction and predict the right label versus a state-of-the-art architecture that uses only the internal patient information. Okay, so with that, I'd like to end. I'll just briefly recall that I discussed novel scientific search engines for biomedical literature. We also discussed biomedical hypothesis generation and clinical outcome prediction by tapping into knowledge in the scientific literature. And that's it, and happy to take questions.
Yeah, thanks, Dr. Ho, for the great talk. Anyone, if you have questions, you can come to the front. Oh, yeah, or if there are questions in the chat, you can raise your hand. Yeah.
Hello.
Hello.
This is Carl. I was wondering if you had any thoughts on some of the some recent language models which also kind of incorporate information retrieval more directly, like retro, for example, from maybe 3 months.
Is this Carl Edwards, by the way?
Yeah.
Great. So we're going to work together in the summer at AI too. But okay. Yeah. So actually, yes, I do have thoughts about that and kind of using that paradigm in this space. I'll just mention one core difference at the moment, which is very interesting in my view, which is that currently language models based on retrieval are evaluated. For example, one of the big tests is question answering, where the answer to the question is typically assumed to be explicit in the text. And here we're looking at a completely different scenario where you want to predict something that doesn't yet exist, like the outcome for a specific patient, or whether some two proteins interact that has not been yet discussed in the literature. So that's one key difference, but I do think that inspiration can be taken from this recent advance in retrieval augmented language models in this space too.
Thank you.
Any questions in the chat? Oh,
Hey, Tom, it's Marty Burke. Really loved your
Oh,
talk.
great.
In the last example with the literature enhanced clinical predictions, have you thought about adding another layer where the algorithm weights the emphasis on the literature data based on the source of the data? For example, when I read the medical literature, if it's a meta-analysis where someone just looks back and reviews all the literature, and it says there may be an association between X and Y, versus a placebo-controlled prospective clinical trial that actually shows that and shows a p-value even, could the algorithm, weight its predictive power based on how good the quality of the data is, like a person would?
Yeah, absolutely. I think that's possible, possible to try at least, and something that I'm interested in exploring. I'll mention one thought about that, which is, in theory at least, not that I think this is completely possible, completely likely, by viewing many examples of patients and relevant literature, the model could learn to capture this kind of signal. And maybe in some cases, there's enough signal in a paper to kind of compensate for certain missing information. But on the other hand, I do completely agree that more explicit kind of encoded prior knowledge or inductive biases, as they are also called, such as the one you mentioned about more explicit structures and signals and metadata about papers, can be directly incorporated into a model to enhance predictive accuracy. I share the intuition that this could be useful.
Great, thanks.
Thank you.
yeah, I think, yeah, we can take one more question. Yeah.
Hi, this is Nick Angelo. So that was a great talk. Thank you. So I was interested in like the novel scientific search engines part. So you kind of talked a bit about how you can kind of capture knowledge that people are, very confident in. So I call those like the known knowns, like the evidence-based knowledge, and then also some amount of knowledge that people are uncertain of. So the kind of the known unknowns. Have you thought about how to capture what people don't know in the literature, but aren't aware or don't explicitly say they don't know? So the kind of unknown unknowns.
Yes, I love the unknown unknowns, as one formerly famous politician in the United States said. But yeah, so unknown unknowns are important. And the way I think about those is by giving researchers the ability to navigate the literature and explore it with interfaces that make it natural to explore the literature. So for example, one search engine I didn't show you, which we call SciSite, also available online, is a kind of interactive exploratory engine where you can start off with, let's say, a specific drug and specific disease you're interested in. And then it'll also surface and show you all kinds of surrounding interesting connections around that specific relationship, like other drugs and diseases, or maybe different kinds of compounds and proteins and genes. Then you can expand around this to discover information in the neighborhood that could also potentially be useful and novel. So that's one way to go about this. Other ways that I look into this is by finding all kinds of analogies across distant domains. So for example, I can take an author in one area and then find authors in a different area that share some partial structural information. Like, for example, they work on the same methods, but in completely different domains of problems. And this kind of trade-off of relevance and novelty, or commonality and contrast, is a way to increase the chance that something is going to be novel to you, but also so unknown, but also with some direct relevance to you. So some of it is going to be kind of more related to your knowledge. So yeah, definitely interesting to explore this further. I think there's all kinds of other paradigms and approaches that can be developed for what is very much an explored problem of how to surface these sparse kind of underexplored areas in space and build bridges across them.
Great, thank you. I was the latter approach you described is what I had in mind, I think, when I was asking that question, because it's kind of like there's discoveries that people are close to making, it may be in different aspects, and being able to tie those together is very, very cool. Thank you.
Thank you.
Yeah, thanks everyone for the question, and thanks to Dr. Hope again for joining us today. Yes, so I think we can move